Fish are hard to track. The current system for estimating fish population and health involves a diver noting the number of fish and their relative size over a specified period of time. This method, while frequently used, involves excessive manpower, provides inaccurate size estimates, and is subject to diver error.
We at FishSense hope to simplify this process with an underwater camera that can automatically identify fish and their length using artificial intelligence. Our current model is functional underwater at a depth of up to 300 feet and has been deployed with REEF divers in Florida. This summer, we also implemented FishSense onboard boats for fisheries research.
However, there are multiple areas that could be improved to help the FishSense make the most accurate measurements possible. This summer, we focused on improving the artificial intelligence algorithm to better detect fish, calibrating the depth cameras for an underwater environment to improve the length estimates, and implementing hardware adjustments requested by the reef divers.
At the start of the summer, our algorithm could detect fish, head, and tail with limited accuracy. The model struggled further with retrieving precise length measurements. Segmentation, or determining exactly where the fish starts and ends, is essential for calculating accurate length. While some previous methods, such as depth-based segmentation, have achieved decent accuracy, this method is computationally expensive and performance drops significantly when we test underwater. This summer, we explored UNIT as an alternate algorithm for segmentation. Unlike the previous segmentation algorithms that have been implemented, UNIT is actually a separate convolutional network. This framework is extremely popular in image processing for its fast and accurate segmentation results.
In order for the AI to measure length correctly, our cameras also need to accurately find the depth at each pixel. While our cameras work well in air, the different index of refraction of seawater and worse contrast underwater create a depth error of 20 to 30%. In an attempt to solve this problem, we tested 5 different forms of calibration to see how they would work underwater. These methods were targeted calibration, target-less calibration, scale calibration, hybrid calibration, and copy calibration from an Intel underwater camera. Of these methods, only 3 were successfully able to complete calibration because of the difficulty of finding the target in an underwater environment. The first, targetless calibration, had a depth percent error of around 2%, but a scaling percent error of 26%. This means that it was able to accurately predict distance from the camera to an object, but couldn't find the lengths of those objects. Scaled calibration, on the other hand, performed poorly at finding depth with an error of 27%, but had a scale error of less than 1%. This means that it was able to find length very accurately, but had a hard time finding distance to objects. We predicted that hybrid calibration, which combined the two, would solve this issue, but it actually performed poorly in both categories, with a 27.5% error for depth and an 8.4% error for scale. Copying the calibration table of the underwater camera directly onto another camera made unusable results.
In addition to providing accurate measurement, our product must be usable for the divers. Following the field deployments in Florida, we've been focusing on upgrading the FishSense hardware based on the first-hand feedback provided by our collaborators. Divers had trouble using the magnetic recording switch as it interacted with their metallic gear. Therefore, this summer we have replaced it with a simple turn switch. We've also streamlined the recording light to display in a more intuitive and easily understood way, and moved it to the rear end cap of the FishSense where it is more easily visible. A depth sensor has also been integrated into the hardware, providing users with valuable depth, pressure, and temperature data from their dive. Final improvements include a real-time clock, which will provide accurate timestamps for all recordings, and the addition of a pressure valve to prevent damages caused by environmental changes. With these additions to the FishSense hardware, we further strive to ensure it is an effective and user-friendly tool for research.
This summer, we also brought FishSense on-board research vessels to help with above-water fish measurements. Fishery research groups like the California Collaborative Fisheries Research Program, or CCFRP, measure fish like these to advise fisheries management and evaluate the performance of marine protected areas.
The current process works like this. A scientist will take a fish to be measured, line up its nose with the front of a measuring board, and then calculate both the fork length, which is the length from the nose to the inside of the tail, and total length, which is the total length of the fish from the nose to the end of the tail. They also check for fish species type and their physical condition. They will then sterilize and tag the fish so it can be identified again and send it back to sea.
To seamlessly integrate our camera with the current process, we built a boat rig that holds the camera above the measuring board, allowing us to capture data as the scientists do their own measurements.
Measuring fish on boats presents a very different set of challenges than those of measuring underwater. Compared to their underwater counterparts, fish captured through on-deck videos are easily differentiable from their backgrounds and will usually be in a fairly clear position to be captured by the camera. To account for these differences, we decided to shift to developing two separate models, one for on-deck and one for underwater. Since we had the opportunity to collect data on deck with our collaborators this summer, our work focused on that model. In order to integrate our system into the researchers' current work, however, we had to overcome the issue of hands obstructing the data. This issue is especially concerning considering some of the data we hope to collect is that of fish volume. With obstructions, this is virtually impossible. Thus, we developed a new protocol by which our researchers capture their data. Using this new protocol, we were able to collect the front and rear halves of the fish separately and stitch them together to then be used for calculations. This allows us to overcome the challenge of obstructions and now calculate fish length and eventually volumetric data as a part of our future work.
Eventually, we hope that our camera will replace the measuring process altogether, so scientists could just point the camera at the fish before sending it back into the ocean. This would minimize the amount of time that fish spend out of the water during measurements, which could decrease mortality rates and simplify the measuring process.
Thanks for watching. Before you go, we would like to acknowledge the team members and collaborators that made this summer possible.
Tell me why our head detection isn't great. Tell me why our depth camera won't calibrate. Tell me why collaborators only say, give us the fish length.